Okay, cool. Now we have the differential relationship. So that means, and remember, u is partial phi partial y, right? So this means for the solution to be self-similar, what we need is partial square phi partial x partial y plus a theta times y times partial square phi partial y square is going to be equal to alpha times partial phi partial y. So this is what it means for the velocity profile to be self-similar. All right. So one thing to be careful here is that it's not justified to apply this same relationship and just to substitute u with phi here. So it is not justified to force the same relationship on phi here, the stream function. Right, because if you think what the stream function is, the stream function is how much flow is in between this point and this point, right? So even if the boundary layer stays exactly the same in the velocity scaling, so even if this b is exactly equal to 1, and if the y direction has been scaled, the phi would be different, right? Okay, so the self-similarity is you can either pose it in one of the two ways, but like you can't have the same relationship for u and phi. Okay, so but this relationship gives me a good tool to get rid of the x derivatives here, right? So it helps me get rid of the partial square phi partial x partial y, because I can substitute partial square phi partial x partial y as a function of something that only depends on y. That's our goal. Our goal is to use the self-similarity to reduce the independent variable x so that I can have an equation that is only in y, that allows me to solve for what is the velocity profile just as a function of y out of these equations, right? So I know the solution has to be self-similar. The question is what kind of shape would be the self-similar solution be, and independent of x, right? Okay, but I have another x derivative here, this. If I can get rid of this and get rid of this, then great. This is a forcing term, right? And in Blasey's equation, what is this actually? For Blasey's boundary layer, it's 0, right? Because the Blasey's is a flat plate and the external velocity is uniform, right? So for Blasey's, this is 0. We'll look at Faulkner scan, which this is non-zero. And we can actually derive what kind of UE it has to be for us to get a self-similar solution. There cannot be anything other than Blasey's or Faulkner scan. So Faulkner scan is the most general self-similar solution you can get out of this equation for a wall boundary condition. Okay, so the only task now is to represent d phi dx into some kind of a derivative of y, right? Okay, so let's try to get this by integrating this function with y, right? So if we integrate both sides of the equation with respect to y, this term becomes what? Yes, this term becomes d phi dx, which is exactly what we need. So we are going to integrate both sides from 0 to a particular y. So here is what we get, and theta y partial square y partial y square, it should be equal to alpha times integration from 0 to y, this, right? Okay, the first term, because we know partial phi partial x is what at y equal to 0? I mean, it's 0, right? Because phi is going to be 0 at y equal to 0. So partial phi partial x is 0. So this term turns out to be just partial, only one partial now, partial phi, partial x at y, right? Now, this term is also easy. What is the integration of d phi dy over y? What is the last term? What is the right-hand side? It's just alpha times phi, right? Because phi is also 0 at 0. So this term turns out to be only phi. This term has some difficulties. Anybody propose how do we integrate the second term on the left? Integration by parts. Yeah, that's right. Great. So we are going to say, okay, this is, let me say here, this is integration of theta times y times d partial theta partial y, right? So this is how you start integration by parts. And then this is going to be split into two terms. One term is the boundary term, that is theta times y times partial phi partial y across the boundary, across from 0 to y, but at 0, y is equal to 0, right? So this is only at y, the boundary term. And then subtract an integral of theta times integral of partial phi partial y times dy. So what is that? That's just the theta phi at y, right? So what we get at the end is partial phi partial x, which is the first term, is equal to, we have alpha phi and theta phi here, so alpha plus theta phi, and we also have this term, which is minus theta y partial phi partial y. That completes our goal of representing partial phi partial x as functions of phi and the derivatives in y. At this point, we have the upper box and lower box. Substitute into this momentum equation in stream function form. We are going to get an equation that has nothing in x.